This is Arvind, Assistant Professor, Department of History, DBS Governance. So in the previous class, I discussed about third unit, that is a parallel operation of alternators. So in this class, I am going to start the fourth unit. Okay. So the fourth unit name is synchronous motors. Okay. So I will start with the what are the topics we are going to cover in this chapter. And now I am going to start the introduction about synchronous motors and some concepts about the synchronous motors. Okay, firstly I will show the index. So these index contains the various topics we are going to cover in this chapter. So firstly I will start with the introduction, and next going to the theory of operation, and next phasor diagram, and next the power flow equations in synchronous motors, and variation of current and power factor with excitation, and V and inverted V curves, and synchronous condensers, and next one is hunting and methods to eliminate hunting, and starting methods of synchronous motor, and synchronous induction motor, and the construction of the synchronous induction motor, and next principle of operation and control of brushless DC motor. These are the various topics we are going to cover in this chapter. So in this class I am going to cover the introduction part and the construction details of the synchronous motor concept. Okay. So first I will start with the definition of the synchronous motor. After that I am going to cover the RMF, and next I am going to cover construction details. Okay. So firstly, coming to the introduction. So our chapter name is synchronous motor. So firstly we have to know what is meant by synchronous motor. Okay. So a device which converts an electrical energy into mechanical energy running at synchronous speed is called as synchronous motor. Okay, a device which converts an electrical energy into a mechanical energy running at synchronous speed is called as synchronous motor. So you know already the motor definition. So motor is a device which converts the electrical energy into mechanical energy. You know that from the motor, and in this one synchronous motor. So same definition is applicable to this one, but one difference is there. So in this one, the speed of the motor is a synchronous speed. That is ns is equal to 120 f by t. Okay. Next, its speed is constant in respect of load. So in the motor, the speed is not a constant; it is changes with respect to the load. But in the synchronous motor, its speed is constant irrespective of loads. Okay, and it is doubly excited machine. The synchronous motor is a doubly excited machine because its field winding is excited from a separate DC source. Okay, because its field winding is excited from a separate DC source. Okay, so this is the introduction, and next coming to the production of rotating magnetic field, that is RMF. So actually this RMF occurs in synchronous motors, that is AC motors. Okay, so that's why I am covering this concept in the synchronous motor. Now in this section we will try to understand the theory behind the production of rotating magnetic field. That means how this RMF, that is the rotating magnetic field, is produced in the synchronous motor, we have to know. So that's why I am taking this concept. Okay, production of rotating magnetic field. So for that one, first we have to take when the three-phase uniformly distributed winding. Okay, here I am taking three-phase winding. Okay, that means it is a three-phase synchronous motor. Okay, so when the three-phase uniformly distributed winding are wound on the stator and supplied with three-phase AC supply. Okay, so here I am considering three-phase uniformly distributed winding. So which are wound on the stator is supplied with three-phase AC supply. So a rotating magnetic flux of constant magnitude, okay, rotating magnetic flux of constant magnitude rotating at synchronous speed is produced. So whenever we given the three-phase AC supply to the stator, so it gets excited and it produces rotating magnetic flux, and some current is flowing through this stator. That's why we have the magnetic flux that to constant magnitude. If these are rotating at synchronous speed is produced. Actually the synchronous speed is approximately 1500 rpm. It is fixed speed. Okay, so that's why I am taking, for example, consider a three-phase two-pole stator having three similar windings. So here I am taking three-phase two-pole stator having three similar windings, that is A dash, B dash and C dash, displaced in space by 120 degrees and supplied with three-phase AC supply. So I will show the diagram, after that you will understand this one. So this is the schematic representation of three-phase two-pole stator winding. Okay, so here I am taking three phases. One is R and another one is Y and another one is B. So R phase, Y phase and B phase, and we have one neutral connection also. Okay, so here I am taking a stator winding. So here I am setting stator winding. It is a distributed winding. So that's why here we are consisting of two poles. One is north pole and another one is south pole. Okay, so in this one it consists of the same winding, that is the same terminal, that is A dash, B dash, C dash, like that. Here we are applying three-phase AC supply. So here A terminal is connected to the R and A dash terminal is connected to neutral and B terminal is connected to Y and B dash terminal is connected to neutral and C terminal is connected to B and C dash terminal is connected to neutral. So like that the connection are provided in this section. Okay, so that's why I am taking a three-phase two-pole stator having three similar windings. That's why I am taking similar windings, that is A dash, B dash, C dash, and these are displaced in space by 120 degrees. So the phase difference between these terminals is 120 degrees and supplied with three-phase AC supply. Okay, that is shown in this diagram. So I already explained this one. And coming to the procedure, how we produce the relative magnetic field in the synchronous motor. So due to current flowing in each phase of the stator, okay, due to current flowing in each phase of the stator produces an alternating flux. Okay, whenever we give the three-phase AC supply to the stators, so that's why we have some current flowing in those phases. Okay, due to current flowing in each phase of the stator produces an alternating flux which is assumed to be sinusoidal in nature. So okay, so here we are considering, we are applying the three-phase supply to the stator winding. So after that we have some current in the stator windings, that means in each phase we have some current. So due to the current in the each phase of the stator produces an alternating flux. Okay, so which is assumed to be sinusoidal in nature. So here we are assuming the production of the flux is in sinusoidal in nature. So that's why here we are taking three phases. So let these fluxes be. In each phase we have alternating flux, that is phi1, phi2 and phi3, and are displaced from each other by 120 degrees. Okay. Next, here we have to find out the instantaneous values of fluxes with respect to time. So from the first phase, that is phi1, that is alternating flux in phase 1. We have phi1 is equal to phi m into sine theta. So here phi m is the maximum value of flux due to any phase. So maximum value of flux due to any phase, that is phi m. So phi m is equal to maximum value of flux due to any phase, that is phi1 is equal to phi m sin theta. And next we have phi2 is equal to, that is the alternating flux in the second phase. So that is B phase, so that is the Y phase, that is the phi2 is equal to phi m into sine of theta minus 120. So I already said that the fluxes are displaced from each other by 120 degrees. So that's why I am taking phi2 is equal to phi m into sine of theta minus 120. And next phi3 is equal to phi m into sine of theta minus 240. Okay, 240 degrees. Like that we are taking the instantaneous values of fluxes with respect to time. Okay. So here the waveforms of these fluxes are shown in figure. So I already said that I am assuming the fluxes are in the sinusoidal in nature. That's why I am taking, for each phase I am taking three waveforms. So each phase consists of sinusoidal waveform. Okay. So here we are taking three phases, that is R by D. So here the graph is drawn between flux with respect to time. Okay. So here we have three waveforms. Three waveforms are in the sinusoidal in nature. Okay. So here first phase, second phase and third phase, this is the maximum flux condition. This is the phi m. Okay. Like that we are taking the instantaneous fluxes in the stator winding, and So I am taking the phasor diagram of these fluxes are shown. So firstly I will take the phasor diagram. So I already said that we have three phases. So in the three phases we are having the alternating flux due to the current flowing in those phases. We have three fluxes, that is phi 1, phi 2 and phi 3 respectively. So these fluxes are drawn like this. So each flux is distributed. Displacement is 120 degrees. The phase displacement is 120 degrees. This is the phasor diagram of those fluxes phi 1, phi 2 and phi 3. Each is displaced by 120 degrees. Okay. Next I am taking, so these three fluxes together gives rise to an effect of rotating flux. Okay. These three fluxes together gives rise to an effect of rotating flux called as rotating magnetic flux, that is RMF, rotating magnetic flux. So the resultant flux phi r, at any instant is the phasor sum of the fluxes of the three phases at that instant. Okay, the resultant flux phi r at any instant is the phasor sum of the fluxes of the three phases at that instant. So here I am considering the four cases. So in the first case I am taking when theta is equal to 0, what will happen, that is I am considering at point 0. Okay, so the phasor diagram is like this. At theta is equal to 0, we have the diagram is like this. So in this one we are taking the three fluxes, but in this one I am taking phi 1 as 0. Okay, and phi 3 and phi 2 we are taking, and by combining these two we have the resultant flux. Okay, so when theta is equal to 0 at point 0, we have the phasor diagram like this. Okay, so here the displacement is 60 degrees. So at theta is equal to 0, the displacement between theta phi 3 and phi 2 is 60 degrees. So here phi 1 is equal to, so I already said that in the previous slides, instantaneous flux values, that is phi 1 is equal to phi m sin theta. So here I am considering theta is equal to 0. So substitute theta value here, that is phi 1 is equal to phi m into sin 0. That means sin 0 means 0. That's why we have phi 1 is equal to 0. And phi 2 is equal to phi m into sin of theta minus 120 degrees. So in the theta place we are substituting 0. That's why we have phi m into sin of 0 minus 120. That is sin minus 120. That is minus root 3 by 2 into phi m. And phi 3 is equal to, from the previous slide, phi m into sin of theta minus 240. So here we are considering theta is equal to 0. That's why I am taking sin of 0 minus 240. That is sin minus 240. That is root 3 by 2 into phi m. Like that we have the values phi 1, phi 2 and phi 3. So phi 1 is 0 and phi 2 is minus root 3 by 2 into phi m, and phi 3 is root 3 by 2 into phi m. So the resultant of phi 2 and phi 3 can be found out by reversing and adding it with phi m. Okay, so the resultant of phi 2 and phi 3 can be found out by reversing and adding it with phi m. So that's why we have the formula, that is the resultant flux is equal to root of minus phi 2. So here the flux value is minus phi 2, that is minus phi 2 whole square plus phi 3 whole square plus 2 into minus phi 2 into phi 3 into cos of 60 degrees. So not 600, it is 60 degrees. So that is equal to root of minus phi 2 means phi 2 whole square plus phi 3 whole square minus 2 into phi 2 into phi 3 into cos 60 degrees. So it is not 600, please correct this. So this is cos 60 degrees. So and we have phi 2 and phi 3 values. Please substitute those values into this formula. So we have root of, in phi 2 place we are substituting minus root 3 by 2 into phi m whole square plus root 3 by 2 into phi m, that is the phi 3 value, that is root 3 by 2 into phi m whole square minus 2 into phi 2 means minus 2 into minus root 3 by 2 into phi m into, so that is phi 2 value is minus root 3 by 2 into phi m into phi 3 value is root 3 by 2 into phi m, that into cos 60 degrees. And finally, after solving this one, we have 1.5 as the value for the resultant flux. That is, the resultant flux phi r is equal to 1.5 into phi m, 1.5 into phi m. That is the first case. When theta is equal to 0, we have the resultant flux value, that is phi r is equal to 1.5 into phi m. And next, coming to the second case, that is when phi is equal to 60 degrees. So if we take the 60 degrees, we have the phasor diagram like this. Here we are taking phi 1 and phi 2 and phi 3 values, but here after taking theta is equal to 60 and substitute in the instantaneous fluxes formulas, we have the values only phi 1 and phi 2, and the phasor sum of this phi 1 and phi 2, we have resultant flux. Okay, so that is, we know the formula, that is phi 1 is equal to, what is the formula? That is phi 1 is equal to phi m into sin theta. So in the theta place I am substituting 60 degrees, that is phi 1 is equal to phi m into sin of 60 degrees. So sin 60 means minus root 3 by 2 into phi m, and phi 2 is equal to, what is the formula? Phi 2 is phi m into sin of theta minus 120. So that is phi 2 is equal to what we have, that is phi m into sin of 60 minus 120. Okay, 60 minus 120. What the value of the one? So 60 minus 120 means 60. Sorry, minus 60. That is phi 2 is equal to root 3 by 2 into phi m, and next phi 3. That is phi 3 is equal to sin of, sorry, phi m into sin of theta minus 180, that is, sorry, 240, that is 60 minus 240, that is we have minus 180. So sin 180 is 0, that is phi 3 is equal to 0 degrees. Okay, and finally we have phi 1 as minus root 3 by 2 into phi m, and phi 2 is root 3 by 2 into phi m, and phi 3 is equal to 0. Substitute these values into resultant flux value, that is phi r is equal to root of phi 1 whole square plus minus phi 2 whole square plus 2 into phi 1 into minus phi 2 into cos 60 degrees, not 60 degrees. So that is equal to root of phi 1 square plus phi 2 square minus 2 phi 1 phi 2 cos 60 degrees. So we have the value, that is phi 1 phi 2 values we have already. So please substitute those values into this one. In this formula we have root of phi 1 value is root 3 by 2 into phi m whole square plus phi 2 value is minus root 3 by 2 into phi m whole square minus 2 into phi 1 value is root 3 by 2 into phi m into minus root 3 by 2 into phi m into cos 60 degrees. So that is equal to resultant flux, that is 1.5 into phi m. So finally we have the resultant flux, that is phi r is equal to 1.5 into phi m, but it has to rotate clockwise through an angle 60 degrees. So in the 0 degrees we have no rotation of the rotor, but here the flux is 1.5 into phi m, so but it has to rotate it clockwise through an angle 60 degrees. So this is for the second case, and next I am taking the third case, that is when phi is equal to 120 degrees, that is at point 2. Okay, so you know the formula of the instantaneous flux of phi 1, phi 2 and phi 3. Take those formulas here. That is phi 1 is equal to phi m into sin theta, and next phi 2 is equal to phi m into sin of theta minus 120, comma phi 3 is equal to phi m into sin of theta minus 240. So substitute the theta value 120 in those instantaneous fluxes values. So that is phi 1 is equal to root 3 by 2 into phi m, and phi 2 is 0, and phi 3 is minus root 3 by 2 into phi m. So based on these values, we have to draw the phasor diagram. So that's why here phi 2 value is, so please ignore the phi 2 value and take phi 3 and phi 1 values. That theta is equal to 120, that is at point 2. We have the phasor diagram like this. So the phi r is the resultant sum of the phi 3 and phi 1. Okay. So that is resultant flux is equal to root of, you know the formula, that is phi 1. Here we are considering two fluxes, that is phi 1 and phi 3. So phi 1 whole square plus minus phi 3 whole square plus 2 into phi1 minus phi3 into cos 60 degrees. So that is equal to root of phi1 square plus phi3 square minus 2 phi1 into phi3 into cos 60 degrees. So that is equal to root of phi1 means root of 3 by 2 into phi m whole square plus phi3 means minus root 3 by 2 into phi m whole square minus 2 into phi 1 means root 3 by 2 into phi m into minus root 3 by 2 into phi m, that is the phi 3 value, into cos 60 degrees, and finally we have the value that is 1.5 into phi m. So hence phi r is equal to 1.5 into phi m and theta is equal to 120 degrees, but has further rotated clockwise through an angle 60 degrees or 100 degrees from the glass. Okay, and next, finally we are going to the fourth case, that is when theta is equal to 180 degrees, that is at point 3. So substitute this theta is equal to 180 degrees in the instantaneous flux value formula, that is phi 1 is equal to phi m into sin theta and phi 2 is equal to phi m into sin of theta minus 120 and phi 3 is equal to phi m into sin of theta minus 240. Okay, please substitute this 180 degrees value in the theta please in the three fluxes, and that one, from that one we have the values, that is phi 1 is equal to 0 degrees and phi 2 is equal to root 3 by 2 into phi m and phi 3 is equal to minus root 3 by 2 into phi m. So please substitute these three values in the resultant flux formula, that is root of phi 2 whole square plus minus phi 3 whole square plus 2 into phi 2 minus phi 3 cos 60 degrees. So that is equal to root of phi 2 whole square plus phi 3 whole square minus 2 into phi 2 into phi 3 into cos 60 degrees. So that is equal to, we know the formula, we know the values of phi 2 and phi 3. Substitute here. So we have, after substitution we have root of phi 2 is root 3 by 2 into phi m whole square plus phi 3 is minus root 3 by 2 into phi m whole square minus 2 into phi 2 value is root 3 by 2 into phi m into phi 3 value is minus root 3 by 2 into phi m into cos 60 degrees. So that is equal to 1.5 into phi m. Hence phi r is equal to 1.5 into phi m, but has further rotated clockwise through an angle 60 degrees or 180 degrees from the start. So based on this theory, we noticed that the rotational magnetic flux, how the rotational magnetic flux is producing in the synchronous motors. Okay, that is RMS. And next, so from the above it is clear that, so few more points to note that, so from the above it is clear that the result, from the four cases it is clear that the resultant flux is of constant magnitude and having value that is 1.5 into phi m, that is phi r is equal to 1.5 into phi m. Okay, the resultant flux is constant in all the cases, that is 1.5 into phi m, and the resultant flux rotates at the synchronous speed, that is ns. You know the formula for the synchronous speed, that is ns is equal to 120 f by p rpm. So here f is equal to supply frequency and p is equal to number of poles. And next, so when three-phase supply is applied to three-phase stator, okay, when three-phase supply is applied to three-phase stator winding, a rotating magnetic flux of constant magnitude rotating at synchronous speed is produced. Okay, so when three-phase supply is applied to three-phase stator winding, a rotating magnetic flux, that is RMF, of constant magnitude rotating at synchronous speed is produced. Okay, this is for the explanation of rotating magnetic flux in the synchronous motors. And next I am going to next topic, that is constructional details of synchronous motor. Okay, constructional details of synchronous motor. So in the synchronous motor, construction is basically similar to rotating field type alternator. Okay, the synchronous motor construction is basically similar to the rotating field type alternator. So it consists of two main parts. So the synchronous motor construction consists of two main parts. One is stator and another one is rotor. Okay, stator and rotor. So we will discuss the stator and rotor briefly here in detail here. So this is the diagram for the construction details of synchronous motor. So here we are consisting two poles, one is north pole and another one is south pole, and we have one stator and rotor. So the stator consists of the slots, which consists of the winding, stator winding. So if you observe this diagram, you will understand. So and we have the rotor, and the rotor consists of the field winding. Okay. So and this field winding is excited by the DC supply. Okay, and the stator winding consists of the three-phase supply. Okay, the rotor winding consists of DC supply, and the stator winding consists of three-phase supply. And we have, it is a salient pole rotor. So here we are taking the rotor, that is a salient pole rotor. So I will explain why we are taking salient pole rotor. Okay. So this is the construction details of synchronous motor. This is the diagram representation. And next, coming to the first one, that is stator. So the armature winding is usually on the stator. So you already know this one. The armature winding is usually on the stator, and so it is called stator winding. Okay, the armature winding is usually on the stator, and so it is called stator winding. So the stator winding consists of a three-phase distributed winding embedded in the slots and excited by a three-phase AC supply. So I already said that the stator winding is excited by the three-phase AC supply. Okay, that's why it's consisting of the three-phase. The stator consisting of the three-phase distributed winding. Those are embedded in the slots and excited by a three-phase AC supply. So this is the explanation for the stator. And coming to the rotor, so in the rotor, the motor has a winding. Okay, the motor has a winding, the field winding. It consists of the field winding, and the construction of which can be salient or non-salient type. So the construction of the rotor will be a salient or non-salient type. So practically, most of the synchronous motors are used salient pole type construction. That's why we are focusing on only salient pole type construction. Okay, practically most of the synchronous motors are used salient pole type construction, and the field winding is excited by a separate DC supply through slip rings. Okay, the field winding is excited by a separate DC supply through slip rings. Okay, like that we are taking this one. And the rotor carries special winding. So actually we know the stator and the rotor windings, that is armature winding and the field winding, but in the synchronous motor we have another type of winding. So that's why I am taking the rotor carries special winding called as damper winding, or this one is also called spiral cage winding. So in addition to the normal field winding, we have special winding, that is damper winding or spiral cage winding. So the damper winding consists of short-circuited copper bars. Okay, the damper winding consists of short-circuited copper bars embedded in the faces of the field poles. Okay, the damper winding consists of short-circuited copper bars embedded in the faces of the field poles. So the function of the winding is to develop starting torque and prevent hunting in a synchronous motor. Okay, the function of the winding, that is the damper winding, is to develop starting torque and prevent hunting in a synchronous motor. Okay, so this is the construction details of synchronous motor. And next we have one more concept, that is magnetic locking. So actually this magnetic locking is the synchronous motor working principle. Okay, so in this one the synchronous motor works on the principle of the magnetic locking. So that is, what is the magnetic locking? I will explain. So here we are taking two poles. Okay, so that means when two unlike poles are brought near to each other, unlike poles is different poles. So when two different poles are brought near each other, that means if the magnets are strong, okay, so there exists a tremendous force of attraction between these two poles. So if the magnets are strong, there exists a tremendous force of attraction between these two poles. Okay, two unlike poles. So in such condition, the two magnets said to be magnetically locked. Okay, in such condition, the two magnets said to be magnetically locked. So if now one of the two magnets is rotated, so actually we have the two magnets, that means we have two poles. So if now one of the two magnets is rotated, the other also rotated in the same direction with the same speed. Okay, the other also rotated in the same direction with the same speed due to the force of attraction, that is due to magnetic locking condition. Okay, so to have the magnetic locking condition, there must exist two unlike poles and magnetic axis of two must be brought very close to each other. Okay, to have the magnetic condition, that means there must exist two unlike poles and magnetic axis of two poles must be brought very close to each other. So this is the principle of magnetic locking. So here I am taking the two unlike poles, that is North Pole and South Pole. So the North Pole coming towards the South and the South Pole to flow, it is going to the towards the North Pole. So at that time there is a tremendous force of attraction. When we have this tremendous force of attraction, when the two magnets are strong, the two poles have the tremendous force of attraction. And I already said that if one magnet is rotating in one direction, the magnet too is also gets rotated in the same direction. So that's why this is the principle of magnetic locking. Okay. So this is the introduction about synchronous motors. Okay, and next in the introduction I am discussing about what is meant by synchronous motor and RMF, that is a rotating magnetic field. Okay, theory of production of rotating magnetic field we discussed it, and next we discussed about the constructional details, and next we discussed about the magnetic locking concept. Okay, and in the next class I am going to discuss working principle of the synchronous motor. Okay, thank you for watching this video.